Okay, so before we get into similarity triangle theorems, y'all remember congruent triangles. We have 5 congruent triangle theorems. The first is side, 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 abbreviated as SSS, side, angle, abbreviated as SAS, angle, side, angle, aka ASA postulate, angle, angle, side, also known as the AAS postulate, and the hypotenuse leg theorem for right triangles. Alright, so what's the difference between congruent triangles and similar triangles? Well, congruent triangles are 2 triangles whose corresponding sides and corresponding angles are congruent. And it's written, for example, as triangle ABC is congruent to triangle DEF. Similar triangles, on the other hand, are 2 triangles whose corresponding angles are congruent, but whose corresponding sides are proportional, not congruent. And for example, it's written as triangle ABC is similar to triangle DEF. Okay, so the first triangle similarity theorem that I'm going to be discussing with you today is the angle-angle postulate, often just abbreviated as the AA postulate, which says if 2 angles of one triangle are congruent to 2 angles of a second triangle, then the triangles are similar. How do we know this? Well, the no-choice theorem tells us that if 2 angles of one triangle, aka here, A and B, are congruent to 2 angles of a second triangle, aka D and E, then the third corresponding angle, which would be here, angle C and angle F, have to be congruent, because all angles of a triangle are out of 180 degrees, and so by substitution and a property of addition, you get that the 2 angles are indeed equal. And if the corresponding angles of 2 triangles are congruent, then they have to have the same shape. And going back to the definition of similarity, similar figures are 2 figures that have the same shape, but not necessarily the same size. And so that's how this postulate was figured out. Okay, so here's how the AA postulate can be particularly useful. So here we have an example where we're given parallelogram ABCD, ABCD, and we're supposed to prove that triangle BFE is similar to triangle CFD. So how are we going to go about doing this? Well, first, as always, we're going to state the given, parallelogram ABCD, reason given. Our second step is going to be to say that segment AB is parallel to segment CD, and this is because of the definition of a parallelogram, which says that opposite sides of a parallelogram are parallel. That's the name. The third step is going to be to say that angle CDF is congruent to angle E. And the reason for this is that here we have 2 parallel lines. BE is an extension of one of those parallel lines, and alternate interior angles, in which here DE is the transversal, are congruent. And so we say that those 2 there are congruent. Step 4 is to say that angle DFC is congruent to angle EFB. And the reason for this is because of the vertical angles theorem, because here we have vertical angles. And of course the last step is to say that the 2 triangles here, BFE and CFD, are similar to each other, and that's because of, hey, what do you know, the AA postulate. So seeing how that is used in action. So the second and final idea that I'll be discussing with you today is theorem 5.1, the first theorem in chapter 5, which says that if a line is parallel to one side of a triangle and intersects the other 2 sides of the triangle in 2 points, then the line cuts off an additional triangle that is similar to the given triangle. So here we have triangle ABC being cut off by DE, which is parallel to BC, and we know that angle B is parallel to angle ADE, and angle AED is congruent to angle C because of parallel lines implying corresponding angles, where AB is the transversal, AC is the transversal here, and obviously the 2 parallel lines DE and BC. Sorry, that looks like an R. That angle APR is congruent to angle ABC. And that's because parallel lines imply corresponding angles, which is what I mentioned in the previous slide, that if you have transversal AB intersecting PR as well as BC, which are parallel to each other, that you're going to be able to use corresponding angles to say that those angles are congruent. The third step is to say that angle A is congruent to itself, and this is because of the reflexive property, so angle A in triangle ABC and angle A in triangle APR. And so the last step is to say that triangle APR is indeed similar to triangle ABC, and this is, hey, what do you know, because of the AA postulate. We have angle A, which is congruent to itself, and angle APR, which is congruent to angle ABC. And so that's the proof for theorem 5.1. And so now here's a couple of examples in which we'll be implementing Theorem 5.1. So here we have given PR is parallel to BC, AR equals 14, PR equals 12, and BC equals 15, as well as the fact that PB equals 4. And we need to find the lengths of AB, AP, and AC. Well, first, let's get back to the Theorem 5.1 itself, which allows us to say that APR here is similar to triangle ABC. And so once we do that, we can then set up proportions, because as we said in the definition of similar triangles, the sides of similar triangles are proportional. So here we have AP over AB equals AR over AC, which equals PR over BC. And then once we set up that proportion, we can use the numbers we have to plug in digits, which then gives us the proportion of AP over AP plus 4 equals 14 over AC, which equals 12 over 15. And so once we do that, we can then use the numbers we have and do some basic algebra, and you should get, if you want to pause the video and do the math yourself, 17.5 for AC, AP equals 16, and AB equals 20.
Now these other triangle similarities are two theorems that state whether two triangles are similar. And the first being side angle side. And this theorem states that when two triangles have corresponding angles that are congruent and corresponding sides with identical ratios, the triangles are then similar. For example, in this triangle, angle A would be corresponding with angle D, and these two angles would be congruent. And these two pairs of sides would have to have equal ratios. For instance, AB over DE would have to be equal to AC over DF. Then these two triangles would be similar. Now the next theorem is side, side, side. And in this instance, we have 3 pairs of corresponding sides. Now these 3 pairs would have to have ratios that are equal as well. For instance, AB over DE would have to be equal to BC over EF and AC over DF. So if these 3 pairs of corresponding sides were equal, have the same ratio, then these two triangles would have to be similar. Okay, now on to our examples. Now our first example, should read the given LP perpendicularly bisects EA and is the midpoint of LP, and P and R trisect at EA. Now we have to prove that these two triangles are similar, and I already wrote down the given, see, and our first statement, second I guess, angle NPE is congruent to LPA because, now since this perpendicular bisects, they're both right angles, so therefore by the right angle theorem that those two angles would be congruent. And now the next step, NP over LP would be equal to 1 over 2. Now let's see. Since N is the midpoint of LP, that would be true because NP is 1/2 of the entire segment. So that would be the midpoint theorem. Midpoint theorem. Let's see. Now, let's see, the next one. EP over PA is equal to 1/2. So let's see, EP. Now, these 3 segments are congruent because they are trisected. So this is congruent to this, is congruent to this. So therefore, if we say this is 1/2 of this segment, we can also say that this is 1/2 of that segment. So therefore, do substitution or midpoint theorem, I'm just going to write down midpoint theorem. Through that, you can state that that is 1/2 of that entire segment. Now because of this, the ratio is 1/2. So the proportion of these sides to that side is 1 to 2. So there, and let's see, and since this angle, it's this angle and these two pairs of sides, that would be the SAS. So therefore, SAS similar, that we prove those two triangles are similar through side angle side. Now the next example, given the two triangles are similar, find AX. Now let's see. Okay, so we don't have to prove that these two triangles are similar because it's given to us that they're similar. So we just got to set up our proportions if we're going to find AX. So let's see, AX over, now you can't put over 5 because it's not the complete segment, so it has to be AC. So it's AX plus 5. So it'd be AX plus 5 is equal to 16 over 24. And if you cross multiply, you'll get 16 AX is equal to 80. plus 80 is equal to 24ax. Now let's see. If you subtract 16 from both sides, you would get 80 equals, can't do basic math, that's me, 8ax. Now if you divide both sides by 8, therefore ax is equal to 10. Okay, now we're on the final example of the video. These are for the side similarity theorem. Now, first example, it says show these two triangles are similar. Now they don't give us any angles, and this is for side, so obviously we're going to start writing some proportions. So 8 over 12, let's see, sorry, brain fart, 14 over 21, and 12 over 18. Now these all have to be equal to the same fraction, and we can clearly see that these are all equal to 2/3. So by the proportion of 2/3, these two triangles are similar. Now on to the next example, asking if these two triangles are similar, and if so, we can write similarity. Now they don't give us any angles again, so by proving that the pairs of sides are proportionally equal to each other, then we can prove that these two triangles are similar. Now let's write the proportions out now. Let's see, 3 over 15. That's a bad 3. Let's see. 2. Do not write 2 over 8 because you have to include this entire side, so it's 2 over 10. 2 over 10. And again, with the entire side included, 4 over 20. So 4 over 20. And this is really laid out for us, so we can clearly see that all these are equal to 1/5. Therefore, yes, these triangles are similar, and similarity is side.